Hello, welcome to lecture 5 of this course. In today's lecture, we are going to conclude our discussion about two-level atom, and also we are going to discuss the so-called density matrix formalism, which is going to be very useful later on. So let us begin. Let us first discuss Dress states in the context of two-level system, and this is a very useful concept. In the last class we saw that, say, we have a two-level atom having ground state represented by this gate Z and the excited represented by this gate E, and transition frequency between this level is omega 0, and a laser pulse having frequency, or laser radiation having frequency omega is getting incident on the atom. This laser radiation may be different from this transition frequency of the atom by some amount, so that is defined as the detuning. And when we have written down the Schrodinger equation for this two-level system, we obtain these equations for the two-level system, these coupled equations for the two-level system in the rotating frame of reference, as we discussed in the last class. So these were the equations that we obtained. Okay, so let me just write it here. So this is what we got in our fourth lecture. All right, now one thing that can be ascertained from our earlier discussion, that when the laser radiation is incident on the atom, two-level atom, this gate Z and E are no longer eigenstates of two-level system when the laser light is incident on the atom, because we have seen from our Rabi flopping discussion that the atom basically go from the ground state to the excited state and excited state to ground state like this. So suppose initially it was in the ground state when we have worked out the probability. So the atom goes from the ground state to the excited state, and after say omega t is equal to pi, the atom would be in the excited state. So if I just draw the probability versus omega t, then this discussion we have already done in great details in the last class. So Rabi oscillations teaches us the fact that this ground state and the excited state are no longer eigenstate of two-level system when laser light is incident on the atom. Now this couple set of differential equation, I can immediately write it in the matrix form. If I write it in the matrix form, let me just show you. I can express this set of couple differential equation like this: Cg Ce tilde, that would be equal to I have here okay, I have here I, you will have 0 here, and then you will have delta, you will have a delta here, and you will have omega by 2 and omega by 2 like this. Okay, so this is what I can write. I hope I am doing it correctly. Okay, there is a minus sign. Okay, so or in other words, I can also write it as minus I by h cross say h tilde Cg Ce tilde here, and h is the effective Hamiltonian and H is equal to H cross 0 here, omega by 2, omega by 2, and I have minus delta. So this is the effective Hamiltonian for this two-level system plus the laser light in the rotating frame of reference. So this atom is now coupled by the so-called Rabi frequency, and in this case here Z and E are there are not eigenstates of this Hamiltonian H. But what we can still do, we can still find out the eigenstates and eigenvalues of this Hamiltonian. We can find eigenvalues of H, and also we can find eigenstates of H tilde. And this Hamiltonian is kind of, it is as if it is dressed by this laser light, so it's a kind of dressed Hamiltonian. And in this formalism, what we are going to say, these eigenstates of the eigenstates of the Hamiltonian H tilde will be known as dressed states. So this is what we are going to do or work out first, to find out the eigenvalues and the eigenstates. To find the eigenvalues, it's very trivial. Let us first find out the eigenvalues. So H tilde, let me, I have again, it is omega by 2 minus delta. Okay, this I can write in this form. If I write it a little bit differently, I can always write this guy as okay, I can write it as, say, H cross delta by 2, H cross omega by 2, H cross omega by 2, then I have minus H cross delta by 2. Then I just have to add here minus S cross delta by 2, 0, 0, and here it would be minus S cross delta by 2. Now you see, by this clever way, if I do it, I know that the eigenvalue of this matrix is simply minus S cross delta by 2. And on the other hand, this already we see from our last to last class, I think third class, we worked out that for the general case, suppose you have here epsilon z is there, then here you have minus epsilon z is there, and epsilon x plus epsilon y, and epsilon x minus I epsilon y. In this general Hamiltonian, the eigenvalues, we actually worked it out, it was plus minus modulus of epsilon, where epsilon is, you have, this is your epsilon x, so we can just write it like this. Okay, so therefore it was simply square root of epsilon x square plus epsilon y square plus epsilon z square. So using this, immediately you see the eigenvalue. So let me just remove this now. So we can immediately write down eigenvalues as this. E is equal to, from here, from this part I get minus H cross delta by 2, and from this part plus minus I will have S cross delta by 2 mod square whole square plus H cross omega by 2 whole square, or better, let me write it as minus S cross delta by 2 plus minus H cross omega tilde by 2, where omega tilde is the generalized Rabi frequency, and it is equal to delta square plus omega square, the Rabi frequency. Okay, so we got the eigenvalues. Okay, we got the eigenvalues. Now the next thing that we have to do is to find out the corresponding eigenvectors. So let us do that. Values corresponding to say E plus, which is minus h cross delta by 2 plus h cross omega tilde by 2. Let me say this is represented by this kth, and I can express any kth vector, any eigenstate or any state as a superposition of basis states. So because I know that this ground state and the excited state, this Z and E are the basis states for the two level system, so therefore I can express it. Let me simply write it as say this is say cos theta here, and these coefficients we are going to work it out. It is cos theta and sin theta. I have taken it in such a way because I know that this coefficient mod square, if I sum them, that has to be equal to 1, and cos square theta plus sin square theta is equal to 1. So this is what I have, and I'm going to work it out. On the other hand, for the other case, for the other eigenvalue, that is minus h cross delta by 2 minus h cross omega tilde by 2. So let us say it is represented by this kth here, and let us say that is a z plus say be, where again I have to find out this coefficient a and b. Now the eigenstates kth plus and kth minus are orthogonal. That means the scalar product of bra plus and kth minus has to be equal to 0. This means that we can write an equation. Bra plus will give us cos theta bra z plus sin theta bra e, and kth minus we have a linear combination of a kz plus b kte is equal to 0, because kz and kt are basis states. So we have this equation a cos theta plus b sin theta is equal to 0. Of course, we have also this constraint that a square plus b square has to be equal to 1. Now from this equation we can take a is equal to say sin theta. Then to satisfy that equation we must have b is equal to minus cos theta. Therefore we have the state minus this kth is equal to sin theta kz minus cos theta kte. And we have also, so already what we are having, all the results we have now, we have this eigenvalues e plus minus is equal to minus h cross delta by 2 plus minus h cross omega tilde by 2, where omega tilde is the generalized Rabi frequency, and that is equal to omega square, that's the Rabi frequency, plus the detuning parameter square delta square. And the states, this eigenstate kth plus and kth minus, we have them as kth plus is equal to cos theta kz plus sin theta kte, and kth minus is equal to sin theta kz minus cos theta kte. And in fact this kth plus and kth minus, these are called the Dres states. Now what about the angle theta? Let us find it out. What about angle theta? Let us find it out in terms of realistic parameters. You see, we have this eigenvalue equation with us, that is h tilde k plus. If we'll get the eigenvalue would be e plus and then the eigen k plus here. If we take kg as the column vector 0 1 and ke as the column vector 1 0, then we can write this equation in the matrix form. And let me write it. The Hamiltonian in the matrix form would be h cross 0 omega by 2 minus delta, and this k plus we'll have it as sine theta cos theta, and we have here e plus is the eigenvalue and this k plus is sine theta cos theta. We can get the equation. One equation is sufficient to solve to find the angle. We have this equation h cross omega by 2 cos theta is equal to e plus sine theta, and from here it is trivial to see that we'll get tan theta is equal to h cross omega by 2 divided by e plus. If I write the value of e plus here, that is minus h cross delta by 2 plus h cross omega by 2. Here I have h cross, actually it is h cross omega tilde by 2, and here I have h cross omega by 2. Then I can have omega Rabi frequency divided by generalized Rabi frequency omega tilde minus the detuning parameter delta. In fact, using this trigonometric formula, tan 2 theta is equal to 2 tan theta divided by 1 minus tan square theta, we can show that tan 2 theta is equal to, it's very trivial and please try it, it would be equal to omega divided by delta. So omega is the Rabi frequency, delta is the detuning parameter, and which are our realistic parameters. And with this condition that here when I am writing it, I am taking theta to be lying between the angle 0 and pi by 2. This angle theta is known as the Stackelberg angle. Okay, now we can see from this eigen values that e plus minus is equal to minus h cross delta by 2 plus minus h cross omega tilde by 2, that coupling to the field, let me write here, this actually implies that coupling to the field causes an avoided crossing in the energy level structure of the atom. Energy level structure of the atom. If you're not getting it, let me show it little bit more clearly. To see that, let us plot E as a function of the detuning parameter delta, eigenvalue E as a function of the detuning parameter delta with, say, the Rabi frequency fixed. We have done similar kind of stuff when we discuss two-level atom. That is a general characteristics of any two-state system. So what we have here, let us say this is E in the y-axis and detuning parameter delta is in the x-axis. First of all, say
we have here, let me consider first the case when there is no coupling. That means the Rabi frequency is 0. Omega is equal to 0. Then E, energy eigenvalue E would be equal to minus h cross delta by 2 plus minus h cross delta by 2. So this means I have E plus is equal to 0 and E minus is equal to minus h cross delta. So for E plus, we'll get, say, this plot, that is E plus is equal to 0. So this is what I'll have, E plus for when Rabi frequency is 0, and E minus minus h cross delta, so it has a negative slope, so I will have a something like this. Okay, I will have here okay, so this is what I'll have. This is for E minus when omega is equal to 0. There is no coupling. Now when the coupling is there, when omega is not equal to 0, then we have E plus minus is equal to minus h cross delta by 2 plus minus h cross omega square plus delta square. Now you see that at delta is equal to 0 here, I will have E plus is equal to, as you can see, we'll have h cross delta. So this would be the point, say. This would be the point here. And for E minus, I will have minus h cross omega. So these are the points, and because of that, I will get a plot of this type. Actually, let me do it, extend it. Okay, so I will have a plot of this type, and this is E plus when omega is not equal to 0, and this one is E minus when omega is not equal to 0. That means when the coupling is there. So you see, there is a clear indication of avoided crossing.
So far in our discussion of two-level system, we discussed a closed two-level system, that is a two-level system not interacting with the surrounding. And for discussion of such system, the state vector formalism is sufficient. We can discuss a two-level system using the so-called density matrix formalism as well. The advantage of this formalism, that is the density matrix formalism, is that we can describe a two-level system interacting with the surrounding as well. That means an open quantum system can be described using the so-called density matrix formalism. So let me discuss density matrix formalism in somewhat details in the context of a two-level system.
We'll discuss density matrix formalism of two-level system or two-level atom. So recall that in the state vector formalism, the state of the two-level system is described by this state vector psi, which we wrote it as a superposition of the basis states, ground state, as well as the excited state. Okay, and when we actually did that in the rotating frame of reference, these coefficients depended on time by these equations, and Ce tilde delta t, we found it as delta Ce tilde minus I omega by 2 Cg. So these equations are basically, we got it from the so-called Schrodinger equations. So in the state vector formalism, the wave function or the state vector as well as the Schrodinger equation is suffice or sufficient to describe the two-level system. And generally this we always can know about the state vector of a quantum system if the quantum system is pure. On the other hand, the state of the TLS, two-level system can also be represented by a quantity, say rho is equal to this kate and this notation. Okay, this is, if you look at it, this is basically an operator by this operator, and this operator is called density operator. It is called density operator, or it is called also known as density matrix. So either you represent the two-level system by in this formalism or this, and the good thing about, as I said, is that this particular way of representing the state of the system has many advantages. One advantage is we'll see later on that by this formalism we can discuss a two-level system interacting with the surrounding very easily. Now if I expand it in terms of this states, as we have written it as a superposition of ground state and the excited state in the rotating frame, if I just write it like this, Cg and Ce, these are complex quantities. So if I take the bra part there, you will get Cg star this Z plus Ce tilde star E. So if you open it up, then let me just expand it. So you will get Cg mod square this kz bra Z. So this, let me just write all the combinations here. You will get Cg Ce tilde star, you will have Z E, then you will have Ce tilde Cz star Ez, and finally you will have Ce tilde mod square EE. Okay, so this is what you have, and this can be written in a matrix form very easily in the basis state, this ground state, and kate Z and kate E. If you take it as your this basis, then you will be able to write it as Cz star Cz Ce tilde, and you just look at these expressions here, and from here again here it would be Ce tilde Cz star, and finally you will have Ce tilde star. Okay, these are the matrix element. If now this is the density matrix, it's an operator, we are now writing it in the matrix form. So in the matrix form, these elements are like this. So if I defined my quantities, say matrix elements rho Z E E S, so first of all say rho Z Z, this first element here rho Z Z, this guy is CZ star, and then this one is rho ZE is equal to CZ CE tilde star, and accordingly I will have rho EZ, that would be CE tilde CZ star, and I will have rho EE, that would be CE and CE star. Okay, so these are the density elements of the density matrix, and it has some physical meaning. First of all, if you see the diagonal elements here, these okay, let me just pick up here. if you look at these diagonal elements of the matrix, this represents the probabilities, right? So rho zz, which is cz mod square, this gives the probability of finding the two level system in the ground state. Rho ee represents the probability of getting the system in the excited state. And so therefore diagonal elements, physically speaking, it represents the population in the either in the ground state or in the excited state. And these particular terms, off diagonal terms, represents the coupling between the ground state and the excited state, and they are actually called coherent terms. Okay, coherences. These are termed as coherences. So these are called populations. They represents populations. On the other hand, these rho ze and rho ez, they represents the coherence, because basically what it says that if rho ze and rho ez are non-zero, then you can create a superposition state between the ground state and the excited state. So more about all these things later on. Now another thing, you can get the time evolution of these density matrix elements as well, and one can very easily get it. Just let me show one example. Say if I want to know how this density matrix element rho ze evolves in time, so you just have to work out this. You have to just expand it and open it up, and if you you will get cz delta t ce star here, and you will have cz ce tilde star delta t. And then if you use these equations here, I think, yeah, here I have written, use these equations, equation 1 and 2. If you use it here, I encourage all of you to do it, and if you do it, you will get this equation for this density matrix element. Delta rho ze delta t would turn out to be I delta rho ze minus I omega by 2 rho ee minus rho zz. Okay, and similarly you will get delta. Actually the other equation is very simple, because what turns out that you can immediately, you see, because rho ze is equal to cz is ce tilde star, and rho z is equal to ce tilde cz star. So this clearly implies that rho ze is equal to rho ez star. Okay, complex conjugate. So therefore this equation is immediately, you just have to take the complex conjugate of this equation, then you will be able to get rho ez. So that would be I delta rho ez plus I omega by 2. You will get rho ee minus rho zz. All right, and similarly you will get equations for delta rho zz delta t. That would be equal to I omega by 2 rho ze minus rho ez. Please kindly verify these equations, and you will get rho ee delta t. That would be equal to minus I by omega 2 rho ze minus rho ez. In fact, if you, let me say this is my equation, say 1, 2, 3 and 4. If you look at equation from 3 and 4, you can immediately see that if I just add 3 and 4, you will get rho zz plus rho ee delta t. That would be simply equal to 0, and this means that the total probability or the population, this implies that rho zz plus rho ee is constant, and which is for a closed two level system is obviously equal to 1. And here these equations that I have written here are for a closed two level system, and these equations are also termed as optical block equation, because I'm considering the interaction of a two level system with a optical radiation. Generally these are called block equation. Okay, and we can incorporate the its interaction of the two level system with the surrounding as well. More I think I will deal those kind of things little bit later. Now these four equations can be written in a very compact form if I introduce. So let us introduce three variables. One variable is, say, u is equal to rho ze plus rho ez. Okay, in fact if you do a close look, this should remind you about the Pauli matrix sigma x. Okay, if you look at the the matrix element here, even in the density matrix case, if you see sigma x is equal to 0 1 1 0, and now if you look at it, rho ze and rho ez, that is basically the off diagonal elements in the, you see, off diagonal elements. So here it is, you have rho zz, rho ze, rho ez, rho ee. So hopefully you can see the connection that you have these off diagonal elements there. So this is something like your Pauli matrices. It should remind you about that. And another variable, say v, I can say that is defined as I rho ez minus rho ze, and it should remind you about the Pauli matrix sigma y, that was 0 minus I 0. Okay, they are not equivalent, but just for it to remind you, they are linked actually. And the other one, last one, w, we can define as rho ee minus rho z, and that is the so-called population difference or population inversion. And sigma z, it should remind you about that, it is 1 0 0 minus 1. Okay, this is population inversion. So using this is population inversion. Using this, these are called block vectors again, and obviously they are related to these Pauli matrices. So u v w are also known as block vector. U v w, they are called block vector. The components of the block vector, three components of the block vector, and one can immediately, using this density matrix equation, one can write the equations for del u del t, equation for del v del t, and equations for del w del t. Okay, it's very simple. You can just, it's some straightforward algebra. Please show that you are going to get it as delta v here, and you will get minus capital omega w minus delta u, and you will get it as omega v. All right, so these are called optical block equation. Also this is called optical block equation for a closed two-level system. So this, nothing extra actually we are learning here, because state vector formalism also told us the same thing, but this is advantage as I said. And now I can define the vector. This is called the block vector, and that has a component along this one direction, one cap, and then say I have this 2 and 3, and I can represent it in a diagram soon in the so-called block sphere. So that's what I'm going to do now. These vectors, these 1 cap, 2 cap, and 3 cap, these are unit vectors, and they are mutually orthogonal to each other in a fictitious three-dimensional space. Let us say vector 1 is, directed along this direction, 2 is along this, and 3 is along this direction. Then I can draw a sphere, three-dimensional fictitious sphere, say like this. Okay, so this should remind you about what we discussed in the generic treatment of two-level system. And this vector s, if I just, okay, let me show one thing. Let me take a time derivative of this vector ds dt. Then if I take it using this block equation, so I have one, okay, let me just show you del u del t plus 2 cap del v del t plus 3 cap del w del t. And I encourage you to just put these equations from here, del u del t, all these values you put there, then you will be able to show that this ds dt will be equal to 1 cap delta plus 3 cap omega v minus 2 cap omega w minus 2 cap delta u. So this is what you will get. Now let me define a vector. Let me define a vector, say q, as this, say 1 cap omega minus 3 cap delta. And if I defined it, actually I can show that q, the cross product of these two vectors q cross s, that if you work it out, then what you are going to get is this. You will be able to show that this would be exactly equal to ds dt. All right, so again, immediately you see that ds dt, okay, let me write here like this, ds dt is equal to q cross s. And similar kind of equations recall from our discussion of the generic two-level system, where we got this equation for the Pauli matrices, right? Or this was S is there also, we said that that's the block vector, and this epsilon vector was there, if you recall, twice E, and then you have this equation in the generic case that we considered earlier. So here this quantity is the role of this quantity is played by this vector q, and immediately you can see that q cross s is perpendicular, okay, perpendicular to s. So the effect of q is only to rotate s. Okay, let me write here the effect of q, the effect of this vector q is to rotate, s about the direction of q. All right, so it actually, what does it mean? That it can only rotate, it cannot lengthen or shorten the vector s. And that is very clear, because if you just take the time derivative of s square, okay, which is, in fact, I can write it as 2s dot ds dt. I hope you get it, because s square is equal to s dot s. So you will get this equation. Now, as I said, that ds dt is equal to q cross s. So immediately you see, because s is perpendicular to this, so therefore the dot product is going to be equal to 0. So therefore this quantity x square is constant. And I want to remind you that we are considering an isolated two-level system as yet. And you can show that s square, if you take it, because s is equal to 1 cap u plus 2 cap v plus 3 cap w, so s square is equal to u square plus v square plus w square. Now if you write u, v and w in terms of these density matrix elements, so say u rho ez plus rho ze whole square, and then accordingly v if you put, then you will get it, because I is there, so minus will be there, so rho ez minus rho ze whole square plus w is rho ee minus rho zz. Okay, and if you open it up and write, okay, you will be able to write it as rho ez rho ze plus rho ee square minus twice rho ee rho zz plus rho zz square. And what I can show you, that if you just write, say, rho ez is equal to ce tilde cz star and so on, then you will be able to show that this is equal to ce tilde mod square plus cz mod square, and which is obviously equal to 1. So s square turns out to be equal to 1, means that this implies that the unit length of block vector, okay, unit length of block vector s is thus because of this thus seen to be equivalent, it is equivalent to the conservation of probability in a two-level system or two-level atom. So whenever s square is equal to 1, the tip of the block vector, so in this diagram I can, if I show, just say tip of the block vector, suppose this is the surface, tip of the block vector always touches the surface of the sphere, and the block vector always lies on the surface of the sphere, okay, and only the angle of this block vector changes as the two-level system evolves in time. So that is equivalent to say that because the population is remaining conserved and we are considering an isolated system, remember, so only this angle that is made by the block vector is going to change with time, and in effect the evolution of two-state density matrix is equivalent to changes in the orientation of the block vector as this is sketched in this particular diagram. So say this block vector, if I just, okay, let me just use this. So block vector can actually move around here in the surface of the sphere, and this is a very useful representation, and many times even in quantum computation and quantum information processing, lot of physics and ideas can be just by could be explained in terms of this block sphere representation. A few comments about the population inversion, which is defined as W is equal to rho E minus rho ZZ. And as you see that this population inversion is associated with this axis 3, and whenever W is equal to 1, which implies that rho EE is equal to 1 and rho ZZ is equal to 0. So therefore what it means is that the atomic population is entirely in the upper level. Atomic population is entirely in the upper level, and block sphere corresponds to a fully inverted atom, and the block vector is directed along the north pole here. And on the other hand, by the same reasoning, if W is equal to -1, the block vector would point towards the south pole. Okay, it would be along the south pole, and the atom is into the lower energy level.
Let me stop for today. In today's class, we learned about the dress-state picture of two-level system, and I also introduced very briefly the concept of density matrix. In the next class, we are going to discuss density matrix in somewhat details, because density matrix is going to be used as a important tool in this course. Thank you.